Hi guys, figured I'd give you a quick update with the system. Um, in this video I'm just going to be demonstrating how the high frequency of my receiver coils and my ground extraction circuit can rapidly recharge those capacitors right there that's hooked up to that receiver coil via a SS560 Scotty diode, very fast switching. I think they're Yeah, so these are the diodes. These are the new diodes that I found to be the most efficient SR560. 60 volt, 5 amp Scotty diodes. So what's occurring is I combine the DC output of, I put a full bridge rectifier composed of those diodes on the L1 of my receiver coils. So, I have three circuits combined here. I have my ground extraction circuit right here. The DC is combined with the DC of that receiver coil and the DC of the super receiver coil. Ideally, because I didn't buy more of those capacitors, they're expensive. It's $15 for two. Those are 10,000 UF 100 volt capacitors. I'll try and zoom in on it. I'm gonna have to get more of them. 100 volt DC, 10,000 UF. They're electrolytics. Ideally, I'll have a twin receiver coil mirroring this one. And what happens is my transmitter consumes about 25 watts, consumes 25 watts to rapidly recharge these caps, and this is what will happen. This battery is not connected in any way to the system. So anyway, this is what occurs. We're only paying for 25 watts, or 20 in this case now, because there is a small power draw when we first start it. It's almost like the space has to get polarized when you turn the system on. As it runs, it reaches an efficiency point, and anyway. So as you see, we charge the system up, right? The system's been running for maybe 20 seconds. I will shut the system off. System is off. I will now show you how much of a charge those capacitors hold and for how long. That is a 200 watt bulb, heat bulb. And it ran for about 5 seconds. 200 watt. So I have to make my capacitor bank even bigger. System is on again. Heat bulb comes up to a slow glow. And this is the type of power that goes into this battery, our supercap bank, to rapidly recharge it. That will then run an inverter which can recharge the system, or can run a household load. Now, I will pulse this and I will show you. So we're only paying for 20 watts, well 25 if you want to be super technical, 25 watts worst case scenario to polarize the space and run our wireless transmitter. In doing so, we wirelessly charge up supercaps, our big DC caps that then pulse into a load. And because we're using 3.6 megahertz, a high frequency, we can rapidly recharge our capacitor bank. So there we go. I will pulse this. I will do 2 seconds on, 4 seconds off. 1, 2. 1, 2, 3, 4. 1, 2. 1, 2, 3, 4. 1, 2. 1, 2, 3, 4. 1, 2. 1, 2, 3, 4. 1, 2. 1, 2, 3, 4. 1, 2. 1 Mississippi, 2 Mississippi, 3 Mississippi, 4 Mississippi. 1 Mississippi, 2 Mississippi. 1 Mississippi, 2 Mississippi, 3 Mississippi, 4. So as you see, we can run that huge bulb in pulses with a duty cycle of 2 seconds on, 4 seconds off. And we're only paying for 20 watts at the transmitter end. Now again, I'll shut this off. off, and I'll show you the stored charge of what these caps are capable of again. There's that bulb. Runs 2 seconds very bright, 4 seconds for a while. And there's the power consumption on it. 200 watts. Now, because we can rapidly recharge caps, because of the high frequency of the system, 3.6 megahertz, we can pulse discharge hundreds of watts very quickly. And that pulse discharging of the capacitors is what allows the system to be self-sustaining. So I figured I'd show that effect. I will now I'll now have that output that was running the bulb hooked back up into my battery here, which then powers our inverter. So this battery gets rapidly recharged from the high frequency. And just have to disconnect this. I was doing refinements to the system and experiments. So 72%. I will turn the system on. We will watch it rapidly recharge this. The caps will charge up and fight the VI curve lag of the battery. As you see, we are charging. And the ideal way to do this would be to have an automatic switch, which would be 2 seconds on, 4 seconds off. I have to get some type of relay that can do that, maybe with a 555 timer, which would trigger a high current switch. And all the power from those caps would dump into our battery. Like, it's powerful. You can see those just high current sparks when I shoot everywhere. Next, I will... Oh, another note, too, that I discovered is if you double layer this plate, like you insulate an aluminum plate with plastic wrap, and then if you add another plate and insulate it with plastic wrap, you can run a wire off each plate. And if you connect the plate to the negative of your battery or DC supercap, it'll charge much more rapidly. So now I will turn the inverter on, which will be running a 40-watt bulb, and we will see how rapidly it can recharge. But first I will be plugging the 40-watt bulb into the meter, so the watt meter, so we can see it. Okay, we are on. Bulb is on. I will stand up. Assuming 36 watts. Battery drops in charge. But the key to take away here is when I disconnect the load by shutting the inverter off, watch how rapidly the high frequency will recharge us. As you see, we just jump back. So I'm going to order a lot more of those caps and make a second receiver coil identical to that one. And keep in mind, the size of this doesn't matter. You can still rapidly recharge these guys even if you switch to a bigger bank like this, which I will be doing. This is just to see if the system can be self-sustaining with a battery, and it can. And the reason this system works is because we're using an insulated metal plate, 2 of them actually, like Tesla even says in his patents, for the harness and utilization of radiant energy. We are using an open high-frequency wireless power system that is highly nonlinear. We are using state-of-the-art efficient fast-switching Scotty diodes. So that's efficient. Our system is open. It has negative resistance. It's in contact with the earth and ambient environment, so that's where our gain in power comes from. We are solid state. This device has no moving parts. It is not a perpetual motion machine. The overzealous institutions love to parrot perpetual motion machines cannot work, and they blanket approach apply those laws to everything. This device is not like that. Once activated, it stimulates excess charge buildup in the metal plate and the receiver circuitry from the ambient environment. And as you see, we are charging, again, very rapidly because of the high frequency. It's all just science. There's nothing magic occurring here. Technically, you need the energy, the input energy to start it, and then it creates a type of avalanche or cascade effect, similar to Tesla's magnifying transformer, where a small action creates a movement of a larger action, and we set forth more potential, and we harness it in the metal plate that's insulated. Light hitting that plate will also build up a charge on it, UV light especially. So that explains that. Again, I'll turn the load on. And if I used my mini inverter, the blue one, not this one, because this one's power hungry, I could actually run an LED bulb here, a 5-watt LED, 5 or 10, while simultaneously recharging the battery here. It's just a 10 amp hour, 12 volt battery. And again, I'll shut the system off and we'll watch it rapidly recharge because of the high frequency. And the really interesting thing I discovered too, like I said, you connect the plate, the wire that comes off your insulated plate, to the negative of your battery or supercap. It'll charge much more rapidly. I'm not sure why that is. The radiant energy is having some kind of effect in the battery because the battery also has plates in it. We're also at risk for overcharging the battery using this because these caps want to charge up to 80 volts DC. So you have to keep an eye on it, and once it says 100%, you disconnect and turn the power off. I need to get a bigger charge controller that can handle that power, and I would also like to use a special relay to pulse charge big battery banks. So like 2 seconds on, 4 seconds off, or whatever. And I need to make that cap bank much bigger, mirror it. I'm thinking of a black box stuffed with these caps, maybe like $200 worth of caps, that'll rapidly recharge and run a load. So that explains that. Again, we'll do another test. Our output is 36 watts. 39 actually. Output is 39 watts. Our input is 21 watts. Because we're only paying for the high frequency switching that rapidly recharges the caps that then dump into this buffer tank which runs your load. And again, we're rapidly recharging. So yeah, that's basically all there is to it. To sum it up, we pay for the trigger switching on our transmitter's input. We pay between 20 to 30 watts for the trigger. Our high frequency of 3.6 megahertz rapidly recharges our DC caps that then dump into this guy, which rapidly recharges the tank, and the tank allows you to run your large loads and make the system self-sustaining. So that's that, and take care, everybody. I also sell these as kits. I sell just the transmitter as a kit with a power supply and a few of these little wireless lights, wherever they are. Can't quite remember where I placed it. It's a little wireless LED receiver light. It's good for testing if the system is on. But yeah, anyway, that's our charge. Say 75% any moment. And keep in mind, I could crank that to 25 or 30 watts and it would charge a lot quicker. And I'm going to try and keep this video under 30 minutes. I mean, under 15 minutes. Again, load on, load off, we recharge. So yeah, that's that, and take care, everybody.